Imagine you get in your car in the morning to come into work. You're low on fuel, so you stop by your favorite gas station to fuel up your tank. Now imagine that before you even get out of your car, you have to put this on, and you have to clear everyone away from the gas station for a quarter-mile radius. If you spill even a single drop of the fuel, you have to get a special hazardous spill kit to clean it all up. By the time that you've finished filling your tank, given the all clear, and gotten back into your work clothes, it's 3 p.m., not your typical day, right? This process is actually very similar to how hydrazine fuels are currently loaded onto many rockets, satellites, and spacecraft. It's time-consuming and expensive. Primarily due to the high performance and long-term stability, hydrazine fuels have been used successfully in rocket propulsion for over 60 years. However, hydrazine is not only toxic, but it's also corrosive, flammable, and a probable carcinogen. Very short exposure to hydrazine can cause death or serious residual injury, even if prompt medical attention is given. Hydrazine has a high vapor pressure. Have you ever spilled gasoline and you remember that smell? That's because gasoline also has a high vapor pressure, and you can smell it when it smells. When it spills, excuse me. So the hydrazine's toxicity makes it very dangerous if it's spilled and vapors are inhaled when loading into the satellite before launch. The safety precautions involve first clearing the launch pad, and then the personnel loading the hydrazine have to wear level A self-contained breathing suits in case the hydrazine is spilled. This is time-consuming, and it costs around $1 million per launch. Between 1968 and 2007, there were over 40 spills associated with loading hydrazine fuels, the largest being 74 gallons in 2005. At the AFRL Rocket Lab, we're developing new liquid propellants to replace hydrazine to make the fuel easier and safer to load. Our goal is to find a hydrazine replacement that can both increase the performance, namely the density-specific impulse, by at least 50%, and also reduce the propulsion system mass by 40%. These improvement goals are directly related to space superiority, resilience, and the sustainment of our space assets. In order to reduce the vapor toxicity of our propellants, our chemists developed ionic liquid propellants. We use chemistry to reduce the melting points of our propellants that is similar to putting salt on the roads to melt the ice, or to making old-fashioned ice cream. Now, ionic liquids are very similar to salt, or sodium chloride, in that they are comprised completely of ions, which are very hard to vaporize. Okay, I want you to imagine the smell from a salt shaker. What does that smell like? Well, it doesn't smell because salt doesn't evaporate. This is why you can put a salt shaker on a table and leave it for years, and while it might clump together into a single frustrating mass, it's not going to evaporate away. But how do we make salt into a liquid? Turns out you have to heat salt to above 800 degrees Celsius in order to get it to melt. Ions really want to stick together, even more so than molecular liquids like water, which is why they have no vapor pressure. Therefore, if they spill, you can simply sweep or wipe them up. In these new ionic liquids, the ions are designed to be big and greasy and floppy so they don't stick together so fiercely like they do in salt. We can reduce their melting points to room temperature and even lower while retaining the benefits of the ionic nature of salt, namely zero vapor pressure. But how do we know which ionic liquids make good propellants? There could be as many as 10 to the 18th different combinations of ionic liquids to choose from. Figuring out where to start is like being told to pick a card from a deck with a trillion cards in it. That might take a while. At the AFRL Rocket Lab, we want to replace hydrazine-based hypergolic bipropellants, which is where two stable liquids, one a fuel and the other an oxidizer, mix and ignite spontaneously. The oxidizer is necessary because fire needs oxygen to burn, and there's no oxygen in space. Here you see an ionic liquid droplet fall into a container of oxidizer and ignition. I love that video. So the main benefit of this is that you can actually turn it on and off like your kitchen faucet. This is in contrast to solid rocket motors where once you light them, they burn until they consume all the fuel and they cannot be turned off. Another advantage of hypergolic bipropellants is that they don't need an external ignition source, which greatly simplifies rocket design. The first hypergolic ionic liquid was developed at the AFRL rocket lab back in 2007. We found that one type of ionic liquid shows hypergolic ignition and has short ignition delay times, a metric that's critical in assessing spacecraft maneuverability and response time. Since then, over 1,100 peer-reviewed articles have been published on this topic, and it remains a topic of intense international interest. Ionic liquids are great for almost every kind of hydrazine replacement. In 2019, a SpaceX Falcon Heavy launched from Kennedy Space Center carried the AFRL's green propellant into orbit. Held within NASA's Green Propellant and Fusion Mission Satellites fuel tanks was the ionic liquid formulation with the very government-sounding acronym Ascent. Not only was this new fuel's performance successful, it provided a 50% increase in density-specific impulse, which is similar to getting a 50% improvement in miles per gallon in your car. On top of that, Ascent showed its softer, gentler side when a fuel occurred during the fueling of the spacecraft. In this case, they only needed paper towels and water to clean this up. There's no clearing of the site, no hazmat suits, no scheduled delays, no millions of dollars wasted. The benefits of the new types of rocket fuels go beyond just better gas mileage and easy environment-friendly cleanup. This also opens up the possibility for a single fuel to power both the low efficiency but high thrust rapid maneuvers and high efficiency, steady, low thrust propulsion that satellite operations demand. On November 15th, 2021, Russia demonstrated their ability to shoot down a satellite by destroying their Cosmos 1408 satellite using an anti-satellite missile. China, India, and Israel also have these anti-satellite capabilities. The threat to our military and communication satellites, typically costing hundreds of millions of dollars each, is no longer merely theoretical. There's also the possible threat of collisions with ever-increasing number of objects in orbit around Earth, including defunct satellites and rocket booster fragments. As of January 2021, there are over 21,000 artificial objects in orbit above the Earth, including 4,450 operational satellites. Between adversarial threats and the increasing possibility of collisions with space junk, it's critical that we have rapid maneuverability capabilities in our strategic satellites. Rapid maneuvers require high thrust, think horsepower, chemical propulsion that can quickly ignite and burn, taking advantage of the rapid release of heat and gases. But this is inefficient and can quickly burn up all the fuel on board. Satellites also require high efficiency propulsion, think miles per gallon, for orbital maintenance and for attitude control without using too much of the limited fuel on board. Current systems have separate fuel tanks and hardware for each propulsion mode, but Ascent has the capability to deliver for both propulsion modes. A single tank of Ascent can power both chemical and electric propulsion, enabling rapid maneuvers when necessary and efficient, slower adjustments over the lifetime of the satellite. This concept of multi-mode can bypass the need for multiple propellant storage systems and reduce the mass and volume of the satellite, enabling larger payloads and longer satellite lifetimes. This multi-mode concept is similar to a hybrid vehicle with a single fuel tank and multiple drivetrain options, sort of an eco mode versus a sport mode. Ascent has a 50% increase in density-specific impulse versus hydrazine. Not only can Ascent potentially be used in any space vehicle, but it gets better mileage and fits into a smaller tank. Imagine getting 50% improvement in your miles per gallon or shrinking your tank by half. This pioneering work has the potential to greatly improve the safety of rocket fuels and has fundamentally changed the culture of how we approach and balance the risks and payoff in propellant design. Ascent not only allows us to streamline the fueling process, get better mileage, shrink our fuel tanks, and reduce the hardware necessary for our strategic satellites. Thank you.